Okay, so with all these things done, we are now ready to see the relationship between addition and positivity. That is, we are going to define positive natural numbers, and we will see how addition interacts with positivity. So, positive natural number is the definition is easy. A natural number that is not equal to 0 is said to be a positive natural number. Is said to be a positive natural number. So it's quite easy because we only have natural numbers, and so far we don't have negatives at all. Any number that is negative, those things have not come yet. So the numbers that are available to us, among them, these are positive. 0 is not considered to be positive. It's neither positive nor negative. The question of negative is not coming. So these are positive natural numbers. So any natural number that is not equal to 0 is said to be positive by definition. Okay. Now, immediately we have a proposition regarding this positivity. 2 to 8. So what this proposition says, if A and B are natural numbers where A is positive, then A plus B is also positive. So if we add two natural numbers, at least one of which is positive, you see the restriction that A is positive is there. B may or may not be positive. We are not concerned about that. We just have the positivity of at least one of them. Then the sum also has to be positive. So we want to prove this. And the proof is, again, we will do this by induction. We apply induction on B, keeping A fixed. Okay, so first of all, note that. So we first have to show the result when B is equal to 0. So note that, let me put the line here. A plus 0, when B is 0, A plus 0 is equal to A. Okay. Keep in mind one more thing, that as we take this path, as we go along this development of natural numbers, we have proved this thing, right? A plus 0 is equal to A, and this is in fact a lemma. it does not come immediately from the definition of addition. But now that we have proved it, we have the result available to us for use, and we will use it. But the point here is that sometimes we may not explicitly mention what we are using, because we are going to prove everything. So if we keep on mentioning everything by their name or by the name of the result, then the proofs will become more and more cluttered. So to avoid that, some obvious things which you know what we are using here, so some of them will go unmentioned. Okay, so this result that we proved earlier, we understand that when we are using it, we are using that result. So some things we are not going to mention. Some of the other things which are less obvious or whose use is less obvious, that we will mention. So here, for example, we will not mention, say, lemma 222, that was the result, right? That a natural number plus 0 is equal to that natural number. So we have this which is positive. A is positive, that is our hypothesis. So in this case, when B is 0, A plus 0 is positive. So this is the basis for our induction. Now, next we assume the induction hypothesis. Assume A plus B is positive for some natural number B. A plus B is positive for some natural number B. We then have to prove that if we replace B by its successor, then also that sum is also positive. Now, A plus B plus plus. Okay, we need to prove, according to the strategy of our induction, we need to prove that this is positive. By lemma 2, 2, 3, if you remember, this is equal to the successor of A plus B. So these uses, here I have used lemma 2, 2, 2, here I have used lemma 2, 2, 3. These uses will go unmentioned. Now this, and hence A plus B plus plus is not equal to 0. Why? It's because A plus B plus plus turns out to be the successor of some natural number, right? And we know that the successor of no natural number is equal to 0. That is the third axiom. So here you can write by axiom 2, 3, because here the reason is not as obvious as the previous ones. So here we have written the justification for this conclusion, and hence this is not equal to 0. That is, A plus B plus plus is positive. This completes the induction. And the proof. So we have proved that if we take the sum of a positive natural number and another natural number which may or may not be positive, the sum is positive. And keep in mind one more thing. I cannot write things like this. because this relation is not available to me. There is no, still we don't have any greater than less than, that notion is still absent from our number system. We will come to that. Since we have now got positivity, we will come to that. Okay, so this one is over. Now it has a corollary which is very important. Corollary, let me have this one. Corollary 2 to 9. So what this one says, if A and B are natural numbers such that their sum is 0, then A is equal to 0 and B is also equal to 0. If the sum of two natural numbers is 0, then both of them have to be 0. Here, however, the proof is not by induction, it's by contradiction. Suppose, so we have to prove that under this condition, both the natural numbers are 0. So we are supposing the opposite, that is, at least one of them is non-zero. Suppose A is not equal to 0 or B is not equal to 0. Let me digress for a moment and tell you why. Okay, here you see, this is the conclusion of the result, right? A is equal to 0 and B is equal to 0. What is the negation of this? A is not equal to 0 or B is not equal to 0. Why? That if you recall from mathematical logic, we have this negation of a statement which is a conjunction. For example, this statement P, A is equal to 0 is P and B is equal to 0 is Q. Negation of this is the same as, is equivalent to negation of P or negation of Q. Conjunction becomes disjunction when we take negation. So that's why we have the negation like this. If you can simply think of it naturally, if A is equal to 0 and B is equal to 0, that is not the case, then at least one of them should be non-zero. So that's why you see that this OR is inclusive OR. Both of them also may be non-zero. So that's why either this is true or this is true or both are true. Okay. So with that out of our way, we now proceed with the proof. If A is not equal to 0, then by this previous result, by proposition 2 to 8, so we have now supposed that at least one of them is non-zero. If A is non-zero, then by proposition 2 to 8, A plus B is also positive. This is not equal to 0. Okay. Which contradicts the hypothesis A plus B is equal to 0. because we are given that a plus b is 0. Assuming that, supposing that a is non-zero leads us to conclude that a plus b is non-zero, so it cannot be the case. A similar contradiction comes from b being non-zero. So our supposition is wrong. That is, we must have both a and b 0. So it's because we have had to use proposition 2 to 8, that's why it's a corollary to that proposition. Okay. Now next we come to another result which will prove very important, and it's all these things are obvious to us, but since we are developing the system, we have to prove all these results. Lemma 2 to 10. Let A be a positive natural number. Then there exists a unique natural number B such that the successor of B is A. Okay. Now we have to prove this, and in the text it's not proved, it's left to us, and this is the second exercise. Exercise 2 to 2. Okay, so this is the second exercise. Now we will prove this by induction. Since we are going to write it as a proof, so we will not write solution, although this will be a solution to this exercise. So most of the results in this text analysis 1 by Terence Tao, they are left to us as exercises with ample hints, of course. So most of them can be solved. So the proof is by induction, but before we start the induction, we have to see exactly what we want to prove. Consider the statement what is the statement Pn about the natural number n. We are going to define a statement Pn, and we will prove that Pn is true by induction on n. Either n is equal to 0 or n is equal to m plus plus for some natural number m. So the thing we want to prove here is not exactly what is given in the statement of the lemma. The lemma asks us to prove that every positive natural number is the successor of some natural number. So that means you see here the variable is this, a positive natural number. But I am not, so I cannot take a equal to 0. So I cannot start induction in the usual way. So I devise a new statement where part of my new statement is what is asked here. But another part of it says that it's equal to 0. So my new statement is either the natural number is 0 or it is the successor of some natural number. Now on this statement I will apply induction. Okay. The advantage of this is that for the basis I don't have to show anything. I already have. When n is 0, the first part of the statement is true, and note that my Pn, this statement Pn, this one, is actually a disjunction. It's an or, something or something else. So a disjunction is true if at least one of the statements used to form the disjunction is true. So the first statement is true when n is 0. So we observe that P of 0 is true. So this comes directly from the definition of P. Assume Pn is true for some natural number n. We then have to prove that Pn plus plus is true, right? Now, okay, by the way, what is the meaning, what is Pn plus plus? If I write it using this definition, it means n plus plus is equal to 0 or n plus plus is equal to m plus plus for some natural number m. I need to show that this is true. Okay, that's what means. That's what says that Pn plus plus is true. This, of course, is, we don't have to bother about this. Look at the second part. I need n plus plus to be the successor of some natural number, but that is evident. No? N plus plus is the successor of n, where n is the natural number. So Pn plus plus is true. Now, n plus plus is the successor of the natural number n. Hence, Pn plus plus is true. Thus, by induction, Pn is true for all natural numbers n. Okay, so actually what is asked, I have not really proved, I have not come to that yet. I have proved my own statement. Now I am going to use this fact that Pn is true for all natural numbers n. Now, what are we given? A is a positive natural number, right? Now, okay, so since A is a positive natural number, now PA is true because Pn is true for every natural number n and A in particular is a natural number, so PA is true. Since A is positive, but additionally what is given? A is not any natural number, A is positive. So because A is positive, PA is true means what? Either A is 0 or A is the successor of some natural number. But A is not 0 because it's given that A is positive. Since A is positive, we have. So that means the other part of the statement has to be true. So A will be the successor of some natural number for some natural number B. Okay, so we have proved that A is the successor of some natural number B, but the proof is not over yet. It's because we have to show that this B is unique. Okay, to prove the uniqueness of B, assume A equal to C++ for some natural number C. Suppose A also happens to be the successor of some natural number C. B is already there, but suppose C is also there. Then B++ is equal to B++ is A, and which is also equal to C++. And this implies B is equal to C by axiom 2.4. Because if the successors of two natural numbers are equal, then the natural numbers must be equal. Or equivalently, if two natural numbers are distinct, then their successors are distinct. So here again we have used axiom 2.4. So we will keep on using these axioms, and after some time we will stop mentioning them also, because their use we will get used to their use. Now the result is proved. This proves the uniqueness of B. Okay. Okay, next we will now come to the question of ordering the natural numbers. That is, which one is larger, which one is smaller. That thing now that will come, the order relation. So we have a definition next. So this is definition. 2, 1, 11. What is the title ordering of the natural numbers? Okay, so the definition says let A and B be two natural numbers. We say A is greater than or equal to B if there exists a natural number C such that A is equal to B plus C. So when we can find a natural number C for which A is equal to B plus C, then we say that A is greater than or equal to B. We denote this fact by writing, either this or this. These two symbols mean the same thing, the same relationship between A and B, and it says that A is greater than or equal to B, and this is the definition. If we can find a C for which this is true, then A is greater than or equal to B. We say A is strictly greater than B if A is greater than or equal to B and A is not equal to B. In this case, we write this symbol or the equivalent one, this symbol. So this is how we have defined the order relation on the set of natural numbers. Okay, or I should not mention sets because we are here to see sets formally. Now, once this definition is given to us, we can use it to formulate more things, or we can try to prove the things with which we are already familiar, which involve this notion, this greater than or equal to relation, or in other words, the order relation. It orders the natural numbers according to their sizes. So, for instance, 8 is greater than 5 because 8 is equal to 5 plus 3. See here 8 is A, 5 is B, and 3 is C, and 8 is not equal to 5. That's why it is strictly greater than 5. Greater than or equal to means you just have something like this. But additionally, if you also have non-equality or inequality, then you write this. Okay. Now, note that n plus plus, okay, n plus plus is equal to n plus 1. You see, we have already proved this before. N plus plus is equal to n plus 1, and n plus plus is not equal to n. It's easy to see why this is the case. Or if you